Good morning to you all. Respected Padma Shri Dr. Mailsamy Anadure sir, Engineer Chandrasekhar Prabhu Desai, Dr. Latha Christie, Engineer Anwar Khan, family members of Institution of Engineers India, faculty members, students, and other participants who have tuned in. NDRF is very glad to present this invited talk in association with Institution of Engineers India, Goa State Center. This morning, we are happy to have Chairman of National Design and Research Forum, Padma Shri Dr. Mailsamy Anadure, who was the Project Director of Chandrayaan-1 and who was the Program Director of Mangalyaan and a renowned space scientist himself. NDRF, as you all know, National Design and Research Forum is a 50-year-old organization. It is a R&D wing of Institution of Engineers India, which is again a 100-year-old organization. I welcome all of you to visit our website, www.ndrf.res.in. And we are into many activities which will be shared by our respected chairman in a while. Once again, I welcome you all, and I welcome Chairman of National Design and Research Forum, Padma Shri Dr. Mailsamy Anadure, to present his opening remarks. Welcome you, sir.
Thank you, Dr. Babu, and good morning to all. Today's special talks chief guest, Dr. Latha Christie, Chandrasekhar Prabhu Desai, Amir Khan, Dr. Babu, General Sundaram, and other colleagues and friends. Yes, to IEI and NDRF, I think most of you, the people here will be knowing. Out of 35, I think majority of them I myself know by name. So, and yes, Dr. Babu has rightly told, today in the digital India, which every forum, individual to the organization, they showcase what they are in the social media and their blogs or websites. Similarly, our NDRF website also is as up to date as what we are talking about. So that way, if you go to the website, definitely it gives what is it. It is also celebrating along with the 100-year centenary celebration when IEA is doing 50th year celebration. It's happening for NDRF. That is coinciding across that. So many of the programs for this last couple of years, many of the programs are going on. One is because of the pandemic, we are visiting from the students all the way to the practicing engineers, various webinars. I think the first time we are having another IEA center, this form. Otherwise, majority of them either some educational institutions or the professional bodies connecting to the students, connecting to the practice engineers. Very many things they have done, and bringing in the people from across India and as well as possibly from outside India also to give the professional touch. What's required either in terms of UAVs or robotic systems, automation, the small satellite systems, and the societal needs point of view things. Then you go for today's thing point of view, 3D engineering. Like that, the spectrum of activities of what's happening today, the overall national design development when connecting that point of view, I think we have taken very many steps. And beyond that, good amount of consortiums of academia and the industry's point of view. In spite of the pandemic being sitting there, of course, the consortium mode was going on in NDRF quite long. But even in a pandemic situation, we have the fundings coming probably slightly different from government agencies. I think we are able to get something from the industries, and the good number of activities are going on in the very IITs, the NIT, even other research institutions like Banana Research Institute, our DRDO. Like that, we are able to connect, and good number of universities also it's happening there. While telling like that, then today's thing is basically one such thing is trying to bring in practice engineers to lessons learned. Especially now we are talking about digital India, and the electronics is a norm. Electronics is being the norm, and things are shrinking more and more, and the capacities keep increasing, requirements are keep increasing. We're talking about 2G, 3G, 4G, 5G is already at the end. So that means what is expected from electronics is to keep increasing, looking ahead. But now you cannot look ahead without looking back, because the lessons learned definitely will help you to go better in forward, and so that we will not make once again whatever possible mistakes, whatever we have done there. And once again, the challenges need not be gone. That means once again reinventing the wheel may not be called for. So that's why this particular topic, whatever it is coming, is from the practicing experts, trying to bring in some sort of flavor of the practicality of lessons learned, how it can help for when you move forward. For example, Dr. Liva told identifying me along with Chandrayaan and Mangalyaan. And you look at that, actually the lessons learned in Chandrayaan and Mangalyaan are also worth to discuss. I think it is taken as some of the research works also elsewhere. Specifically look at here, Mangalyaan had a unique history of success. The first attempt to succeeding anybody in any space organization. US has succeeded only in 5th attempt. Russia had only 9th attempt. Japan had to succeed. China had to succeed. That means out of 51 attempts, only 21 succeeded. 30 times they failed. There's a big lessons learned. And that's the 52nd mission when the Mangalyaan has gone. It succeeded because of what are all the lessons learned from the previous 30 failures, previous 30 setbacks. I think that is the major crux of the success, how it has happened with the very, very less budget and the very, very shorter ambitious schedule. We succeeded means it is not alone, but of course, not everybody has come and helped. But what helped is the failures have helped, okay? The lessons learned from the failures have helped. Even the India's, the history of the aerospace, starting from Kalam's SLV, the first failure, has given a huge lessons afterwards to come back in a big way. PSLV first failure has given afterwards, undisputed success of PSLV happened. The lesson learned from the PSLV. So of course, lessons learned need not be very, very lesson. Basically, the setback would have been costlier. But when you're looking at the lesson back, probably this, if somebody could have done some other better way, it not only that particular issue, similar issues also can avoid. I think with respect to PSLV, how a software can overflow, in a computational overflow, spoiled one big mission. Afterwards, see to that how a simulation or computation will be following, what are the limits you have to see, in the testing point of view, how you have to follow. It's the test philosophy itself got changed. It is not only that particular instruction alone getting changed, it is the way in which you do the testing of the whole system, simulation of the whole system, and what you are expected of the system, extreme, it got changed. And that's how, so the lessons learned and the challenges are faced, the previous things will help in a long way, not only if you want to repeat the same similar item. It is even to go forward, that will help that way. So that way it is worthwhile, both IEI, Goa and NDRF combinedly bringing an expert to give in a documented way, Dr. Latha Christie telling the lessons learned and challenges. So that way, it's my best wishes. This also comes along with when the National Design and Research and Development happening on. So these lessons learned and challenges will help in a long way. So with this small note, I leave it to Dr. Latha Christie to come, and with a small intro, I think we will start for the lecture. Thank you and best wishes.
Thank you very much, Padma Shri Dr. Mailswamy Annadurai, for your opening remarks. So now I would request Dr. Latha Christie to give her invited talk on lessons learned and challenges faced during the design and development of electronic systems. But before she starts her talk, I would like to give a brief introduction to Dr. Latha Christie. She is a senior scientist with more than 33 years of experience, and presently the Associate Director at Microwave Tube Research and Development Center, DRDO, Ministry of Defense, Bangalore. After graduating in Electronics and Communication Engineering from Government College of Engineering, Tamil Nadu with honors, she completed her Master's and PhD in Aerospace Engineering from IISc Bangalore. Her research interests are in the field of microwaves and computational electromagnetism. She completed her International Executive Diploma in Project Management from I2P2M in collaboration with George Washington University School of Business, Washington, D.C., USA. She received the prestigious Professor Satish Dhawan Award for Engineers instituted by the Government of Karnataka for outstanding achievements in the field of engineering sciences for the year 2014. And this was awarded by the Chief Minister. Other awards that she received include the Agni Award for Excellence in Self-Reliance and the Best Technical Paper Award for papers submitted at various conferences. Rashtriya Vidyalaya Engineering College, Bangalore conferred on her a citation of honor for her distinguished achievements and contribution in the field of microwave engineering and technology in India on the World Telecommunication and Information Society Day. She also received the President's Scout Award during her school days and has guided many graduating students. She has filed a patent and has more than 70 publications in international journals and conferences. She has authored over 4 books. She is also the host of the Science and Religion web series called The Grand Cosmic Story. So I would request Dr. Latha Christie to give her talk.
Thank you so much, Dr. Delhi Babu, for inviting me to speak on this important topic. I'm so privileged to listen to the introduction by the moon man of ISRO, Mileswamy Annadurai. This December 4th, I have completed exactly 33 years of my life as a scientist with DRDO. I have been working on the design and development of vacuum electronic devices, which are the backbone of radar systems, missiles, airborne radars, satellite communications, electronic countermeasures, and so on. Even the RF system of Chandrayaan-2 lunar mission of ISRO uses an S-band transmitter and an X-band transmitter for payload data transmission to the Indian Deep Space Network. So many of the satellites are using this vacuum electron devices. Vacuum electronics is a very specialized subject. Being in the design and development of such a specialized field for more than 3 decades with various teams and with various projects, I'm here to present before you some of the lessons that I have learned and also some of the challenges that I have faced in the process of the design and development of microwave tubes. On November 12, 2014, space probe Rosetta, built by the European Space Agency, performed the first successful landing on a comet more than 475 million kilometers away from the Earth. The probe transmitted scientific data to Earth that helped us to understand the history of the solar system, as well as it showed the stunning images of the comet. This historic achievement was met thanks to years of developing critical systems, one of them being the communication system consisting of an S-band, X-band traveling wave tube with power ranges from around 100 watts and 30 watts, enabling the mission to transmit data back to Earth. The success of a mission depends crucially on the spacecraft capacity to transmit data across the vacuum of space with enough power to be captured on the ground. Again, it's a 12 watts X-band TWT amplifier that helped New Horizon of NASA mission to boldly go where no one has gone before, to the dwarf planet Pluto and its moons and other objects in the Kuiper Belt. And it sent pictures from such a distant place. Similarly, Cassini mission that had been in Saturn's orbit for 13 years sent 635 gigabytes of data and 453,000 photos to Earth with the help of continuously operating 20 watts, 8.4 to 8.45 gigahertz amplifiers. Voyager 1, that has been launched around 43 years before, is famous for taking its breathtaking image of our Earth, famously called as the pale blue dot by Carl Sagan. is performing its journey at more than 21 billion kilometers away from the Earth in the interstellar space. And you know, it is the longest telecommunication range ever done. It's currently the farthest man-made object still in communication with us, thanks to its 3 TWTAs, 1 in the S-band and 2 in the X-band. The signal takes 19 hours to reach us from the probe and is captured by a worldwide network of tracking facilities belonging to the NASA Deep Space Network. Even the latest James Webb Space Telescope uses Ka-band traveling wave tube. Telecommunication systems mainly consist of an antenna, a receiver, and a transmitter. Inside the transmitter, we need a device that amplifies radio waves enough for us to communicate with spacecrafts, even at more than billions of kilometers. This wave amplifier meets a large number of criteria to be operational in space. For data emission, it needs to reach high signal amplitude with very low noise, and also it needs a large bandwidth at high frequency corresponding to the amount of transmitted information. Lastly, this device needs to resist the shocks of its rocket launch and to operate for years in the dangers of space, in particular in aggressive radiations. All those conditions are fulfilled by the traveling wave tube. Today, this device remains at the cutting edge and still contributes to transmissions for major satellites and space probes for inter-satellite communications, and also in high-performance radar applications, including atmospheric studies, space debris detection, precise tracking, and high-resolution imaging. This is also used in electronic warfare, electronic countermeasures, planes, ships, transponders, and so on. TWT might not be the most powerful vacuum electron device, but its main feature is its large bandwidth and its excellent power efficiency, ideal for long-range communications. They are also exceptional due to their on-orbit reliability and high power efficiency. I feel it's a great privilege for me to work in such high specialty fields. Today, I would like to present the lessons learned and the challenges faced both technically and managerially in my workplace. Since both students and senior scientists are present in this meeting, I would like to present both the technical and the managerial aspects that I have learned during the course of my workplace, the work life, and also the challenges I faced. I would like to speak on these topics. I would interlace and speak lessons learned, how if we don't adapt, we might die, because that's a famous adage, adapt or die. So be a continuous learner, and how to develop a growth mindset, how to be resilient, how to be gritty, and how to change our leadership style as per the situations. And what are the challenges faced by being in a multidisciplinary project, and how I learned to lead the team, and how I learned to adjust with different leaders, and what are the problems that were faced by working women, and all these things I would just touch upon first. And I'm going to speak in depth about the technical details. So the first topic, adapt to latest technical trends. So we know that microwave devices has plenty of applications like radars, long range and high resolution radar, ground probing radar, space debris radar that are used to find the space debris that can destroy satellites and other space probes, and communication, high information density with deep space, satellite communication, electronic warfare, missile guidance, active denial, directed energy weapons, and what else? Advanced electron accelerators, fusion energy research, industrial heating, and material processing. Everywhere we need microwave tubes. So this microwave tubes has gone through a lot of changes. Starting from the beginning of the 19th century, it has gone through. Today, technology changes at lightning speed. Change is inevitable, not only in life, but also in work too. As long as the people and the technology are progressing, so should the research and development that's happening around them. Hughes defined change as any alteration in the status quo. Change makers don't like the status quo. They don't simply sit, but they do something about it. Most of us desire change, but we don't become change makers sometimes because we think perhaps it is difficult or perhaps it's somebody's job. Change makers are relentless. They pursue their goal by using a combination of knowledge, resources, determination, pushing until their vision comes true. So they are personally connected and passionate about the issue. So we need such change makers in every organization, and we need such changes in technologies. A microwave tube is one of the critical technology, and because we can see it is used in many of these applications. So now let us first see how this microwave tube technology has changed over the years and how we need to adapt to the changes that is going to come ahead. So first, let me take you through a storyline of microwave technologies. You know, all of us know that electromagnetic spectrum extends from below the low frequencies used for modern radio telecommunications to gamma radiation at the higher frequency end, thereby covering wavelengths from thousands of kilometers down to a fraction of the size of an atom. The types of electromagnetic radiation are broadly classified as radio waves, microwave radiation, terahertz radiation, infrared radiation, visible radiation, ultraviolet, X-ray, gamma ray. This spectrum is the foundation of our information age and our modern world. The historic foundation of this spectrum was laid in 1861 when James Clerk Maxwell, a Scottish physicist, published the first part of his paper, of his 4-part paper entitled On Physical Lines of Force. Sprinkled amidst the prose in the philosophical magazine were equations that revealed electricity, magnetism, and light are different manifestations of the same phenomena. So he said that his aim was initially to forge a mathematical link between electricity and magnetism that would capture the previous experimental results available. But then he realized that varying the strength of an electric field would generate a changing magnetic field, even in empty space with no moving electric charges to speak of. And he also wondered whether the two fields, electric and magnetic, would nudge each other along in a self-perpetuating wave-like manner. And his calculations made clear that they could. So he plugged the relevant values which had been recently obtained by experimenters in Germany into his equations. Out popped Fizeau's figure for the speed of light. Convinced that this was no accident, Maxwell went on to suggest that light is an electromagnetic wave. Physics had got its first unified theory. Maxwell's greatness lies in showing that nature ought to be taken at face value and that she can be cajoled into revealing her hidden charms so long as the entreaties are whispered in mathematical verse. In doing so, he paved the way for the pursuit of physicists' holy grail, the grand unified theory, a set of equations, the 4 golden laws, which would explain all there is to know about physical reality. Though James Clerk Maxwell, using his famous equation, he brought in existence of the invisible electromagnetic wave, the story began only in 1887 by Heinrich Hertz. Heinrich Hertz became the first to demonstrate the existence of such waves by building an apparatus that produced and detected microwaves in the ultra-high frequency region. Hertz recognized that the result of his experiment validated Maxwell's prediction, but he did not see any practical application for these invisible waves. The gestation of Hertz's scientific discoveries has helped the comforts of pleasures of this 21st century life. 6 years later, we can see Marconi built one of the first radio transmitters with a range of 100 meters, and then on 12th December 1901, he established the transatlantic communication over a distance of 3,500 kilometers that won him worldwide fame. Signals from a high-power spark transmitter in England had been headed into space when it was reflected of the ionosphere and bounce back down to Canada. Earth's ionosphere reflects waves with a frequency less than 300 megahertz, wiping out limitations due to Earth's curvature. But this application is extremely sensitive to weather conditions. Thanks to this, BBC was able to broadcast radio from London over Europe during World War II. As early as 1900, Tesla proposed one of the first applications for powerful radio waves. He suggested radio waves can detect objects, and then radar was born. But at that time, they didn't have any ways to produce electromagnetic waves. Immediately, understanding this limitation, numerous efforts were started and to develop the technology across Europe, United States, Soviet Union between 1920 and 1940. In 1932, a major discovery by Carl Jansky of Bell Labs revealed the stars and other objects in space radiated radio waves, and then radio astronomy was born. But scientists needed giant antennas to detect long wavelength radio waves from space. However, the history of vacuum tubes started in the late 19th century with the discovery of thermionic emission, and the first practical tube was credited to Lee D. Forrest. He invented the triode in 1906. Triode is the only device available in those days for radio frequency community. It's a transit time based device in which the finite transit time of the electron is comparable to the period of the alternating voltage between the electrodes. Its improved variants were developed like tetrodes. Those tetrodes are still in use in some of the applications like radio, TV broadcasting, induction heating applications in industry, and accelerator applications. So the new invention of electron tubes paved the way for further developments in radio and wireless transmission in the first 2 decades of the 1900s. Radar and antenna technology started to bloom. But these electron tubes, the triodes and tetrodes, were not capable of delivering very high powers. Their power levels decreased rapidly at higher frequency because of limitations like transit time effects and lead inductance and inter-electrode capacitance and gain bandwidth limitations. In 1921, American physicist Albert Hull invented the magnetron, which is one of the oldest members of the microwave tubes family. It's a crossed field device in which the potential energy of the electrons is transferred to the wave. It's an M-type device because the electric and magnetic fields are perpendicular to each other and also perpendicular to the direction of propagation. And later, an American engineer by the name Percy Penzer found that an operating microwave tube melted the candy bar in his pocket. He ended up patenting the idea of cooking with microwaves in 1945. The first microwave oven designed for the home applications was marketed in 1955. It's estimated that there are around hundreds of millions of microwave ovens in the world, and each one has at least one magnetron. These 70 to 85% efficient tubes typically provide 0.9 to 1.4 kilowatts of CW power at 2.45 gigahertz, all for an unit price of around $50. Cavity magnetrons were the essential element in early radar systems and had a profound impact on the outcome of the Second World War. Many historical accounts say that the radar was the reason for the victory of the Allies in World War II. Since World War II, radar has become very useful in a great variety of applications. Its ability to function in an all-weather environment at long ranges is unmatched by any other available sensor. It can be fitted to ground, ship, air, or even space-based platforms. In military applications, radar is used in ground-penetrating air surveillance, anti-missile systems, fire control. In the air, radar is used for controlling air traffic, anti-collision systems, and altimetry. On the sea, radar is used in ocean surveillance. A functional radar consists of 4 basic elements: a transmitter, a highly directional antenna, a receiver, and a display. The transmitter produces intense pulses of microwave electromagnetic energy at short intervals. The pulses are propagated outward in a narrow beam from the antenna and strike targets at various distances. The reflected signal or echoes are picked up by the antenna shortly after the pulse is transmitted. The time gap between the transmission and the receipt of the echo is directly proportional to the distance of the target from the radar. So the farther the target, longer is the time before the echo is received. This is the function of the radars. So this helped, as I said, the Allies to win the war. The onset of the two world wars pushed the strategic needs to higher frequencies and higher power levels, because at the lower frequency, it was continuously becoming congested. This motivated the quest for still higher power, still higher frequency, and the need to produce microwave sources. So in 1937, Varian brothers developed the earliest versions of Klystron amplifier. And after 5 years, TWT was invented. The fatherhood for TWT was often granted to an Austrian refugee, Rudolf Kampfner, when he was secretly working for the British Admiralty. But actually, the tube's history is different. It was consequently discovered by 3 people. The history of the TWT dates much before Rudolf Kampfner, when Andre Heffman came to California from China in 1931. At that time, nobody knew how to efficiently amplify microwave signals whose frequency was higher than that of vacuum electron beams, because microwave signals frequency is so higher. So one day when Heff was observing the surface on the Santa Monica beach, he was observing them intently, and then he understood that if the longitudinal component of the board velocity and the phase velocity of the wave coincided, you can efficiently use the wave energy. The young engineer began to explore a tube in which a high frequency wave propagates in a spiral system, whereas electrons move parallel to the spiral axis. The wave velocity along the spiral axis decreases, and so it turns out to be equal to the velocity of the slowly moving electrons. So now when these two are in synchronism, the kinetic energy of the beam can be given to the wave, and the wave can be amplified. So he registered his first patent for the tube in October 1933, and he used the word traveling wave. This was the first example for the tube, for a device, and later in March 1934, he sold this patent to Radio Corporation of America for an amount of $12,000 US. But again, the TWT was rediscovered by Niels Lindenblad in 1936. He too registered a patent. So then he was working, and finally, again a third time, it was discovered by Rudolf Kampfner. Kampfner was working during the day with Klystrons, and in the evenings, he developed his own various devices. One of them was a TWT. His Klystron had the limitation. If you see here, this is the top one is a Klystron. The Klystron had the limitation of narrow bandwidth because amplification is restricted to the resonant frequency of the cavities. So then idea came to him to couple the individual cavities in a multi-cavity Klystron to a common transmission line so that there may be a continuous in-phase interaction between the beam and the circuit. Eventually, this led to the development of traveling wave tube amplifier. So now this is a typical traveling wave tube amplifier. You have an electron gun that sends the electron beam, and you have a slow structure that slows the wave down. And then you have this coupler and output coupler, both input and output couplers, and then the magnetic field to focus the electron beam, and finally the collector to collect the spent electron beam. And after this traveling wave tube, we can see superconductivity made a great stride in the 60s and 70s. And so it helped in providing a few tens of Teslas of magnetic field. That's why it gave birth to a to the birth of new devices like fast wave devices like gyrotron. So gyrotron was born because of the invention of superconducting magnets. So coming to gyrotron is a fast wave device. We saw TWT is a slow wave device because the electron wave is slowed down to that of the electron beam velocity, whereas a gyrotron is a fast wave device. In gyrotron, the electron gun emits hollow tubular beam of electrons, which is accelerated by a high voltage anode, which then travels through a large tubular resonant cavity structure in a strong axial magnetic field, which is usually created by a superconducting magnet around the tube. The field causes the electrons to move helically in tight circles. You can see here the field causes the electrons to move helically in tight circles around the magnetic field lines as they travel lengthwise through the tube. As in the other linear beam microwave tubes, the energy of the output electromagnetic wave comes from the kinetic energy of the electron beam. In the region before the resonant cavity where the magnetic field strength is increasing, it compresses the electron beam, converting the longitudinal drift velocity to transverse orbital velocity. Due to the standing waves in the resonant cavity, the electrons become bunched in phase and emit coherent radiation. The electron speed in a gyrotron is slightly relativistic. The spent electron beam is absorbed by the collector electrode at the end of the tube. This tube has an important advantage, namely the area where interaction of electromagnetic wave and electron beam occurs is of a simple geometry and does not require delay lines like klystron, magnetrons, or TWTs. So because the delay lines has a delicate structure, and those things have resonators, and that limited their use to high frequencies and high power levels. But gyrotrons can be used at high frequency and high power levels. Another advantage is that it has a relatively high efficiency, and the power they can generate, especially in wavelength around in the millimetric wave frequencies. The power generated by gyrotrons may be several orders of magnitude greater than the power generated by a semiconductor device. So now coming to this, we can classify amplifier and oscillator. Each one we can classify as a slow wave device and a fast wave device. And you can see here, there are so many microwave devices: helix TWT, coupled cavity, multi-beam klystron, extended interaction klystron, gyro TWT, gyro klystron, magnetron, relativistic magnetron, relativistic backward wave oscillator, vecators, gyrotron. All these are different forms. So now you can see here, you will get a picture. If you want to adapt to changes, we need to get technologies in various fields, because for some application you need very high bandwidth, for some application you need high power, for some you need both high power and wide bandwidth. And so all these things put constraint, and we need to choose which device we had to use. So coming to this one now, we saw about this vacuum electron devices. Parallelly, another technology was popping up, the solid state technology. In the 1950s and the 1960s, the invention and spread of transistor technology also opened the way for many applications in the field of bipolar transistors and MOSFETs and so on. And they were delivering several tens of watts of up to frequencies of around 1.5 gigahertz, recently around 1 kilowatt per unit with 6th generation MOSFETs. RF solid-state amplifiers are increasingly used in broadcast applications, in particular in digital modulation and so on. 10 kilowatts, 20 kilowatts are obtained by combining several modules. And also the availability of gallium arsenide, silicon carbide, and gallium nitride-based broadband and medium power solid-state amplifiers up to W band affected the domain of microwave tubes. So solid-state electronics began to overtake vacuum tubes and radios and computers and other electronic and radio frequency gadgetries around 60 years back. But the ensuing sea change in electronics came not because of the intrinsic advantage of semiconductors, but because the engineers gained the ability to mass produce and combine transistors in integrated circuits by chemically engraving or etching a silicon wafer with the appropriate pattern. As the technology of integrated circuit fabrication progressed, more and more transistors could be squeezed into microchips, allowing the circuitry to become more elaborate from one generation to the next. The electronics also became faster without costing anything, not much. That speed benefit stemmed from the fact that as the transistors became smaller, electrons moving through them had to travel increasingly shorter distance between the source and the drain, allowing each transistor to be turned on and off more quickly. Vacuum tubes, if you see on the other hand, were big and bulky and had to be fabricated individually by mechanical machining. So given vacuum, with all these things, we can see vacuum tubes are still in the market. Do you wonder why? Let me explain. In September 1976, in the midst of the Cold War, Viktor Ivanovich Belenko, a Soviet pilot, veered off course from a training flight over Siberia in his MiG-25, and he flew low and fast across the Sea of Japan and landed the plane at a civilian airport in Hokkaido with just 30 seconds of fuel remaining. His dramatic defection was a boon for US military analysts. They, for the first time, had an opportunity to examine so close this high-speed Soviet fighter. They never thought that they will get a chance. As per them, it is one of the world's most capable aircraft. But what they discovered astonished them. First of all, the airframe was more crudely built than those of their fighters because they were made of steel rather than titanium. What's more, they found the plane's avionics base to be filled with equipment based on vacuum devices rather than transistors. Because in US, most of the time, they switched on to solid-state devices. So that's when they understood vacuum devices made these aircraft sturdy. However, the Iraq war that started in 2003 and lasted for almost 7 years made the US and allies to encounter remotely triggered improved explosive device. So the government ordered the production of small jammers that can block an IED from detonating. By preventing the radio signals from reaching the radio trigger used to detonate the IED, by jamming the electromagnetic energy, it is possible. That's why they invested in gallium nitride technology. And in the last decade, this technology has grown to such an extent that gallium nitride power amplifiers seems to blow a death knell to TWTs. Gallium nitride is a wide band gap compound semiconductor material that delivers higher power density per millimeter of gate length over a broader frequency range than any other solid state technology. Yes, it depends on many factors like frequency, bandwidth, and how many devices are needed to reach the same output as a TWT, because it needs a multiple transistors to match the output power of a single TWT. While it is possible to sum the contribution of many power transistors to achieve it, it's sacrificing some of the power to the insertion loss of the power combiners. Presently, gallium nitride devices are available as commercial products in S, C, X, and Q band, and newer configuration are promising for gain with cutoff frequency up to 150 megahertz and maximum oscillation frequency up to 230 gigahertz with 100 nanometer gate length. So now, but the single device performance of solid-state amplifier is no match to that of TWT. So let me give you an example. Let's take one solid-state amplifier. Let it be a metal oxide semiconductor field effect transistor, MOSFET, and compare it with a microwave tube. The voltage applied to one terminal, that is from cathode to anode in a vacuum electron tube and from source to drain in a MOSFET, controls the amount of current flowing between them. This ability is what allows each of these devices to function as an amplifier. How electric current flows in a vacuum tube is much different from how it flows in a transistor. Vacuum tubes rely on a process called thermionic emission. Heating the cathode causes it to shed electrons into the surrounding vacuum. The current in transistors, on the other hand, comes from the drift and diffusion of electrons or holes between the source and the drain to the solid semiconducting material that separates them. Vacuum tubes gave way to solid state in some applications because of some of the advantages of semiconductors like lower cost, much smaller size, superior life sometimes, efficiency, ruggedness, reliability, and consistency. However, when considered purely as a medium for transporting charge, vacuum wins over semiconductors. Electrons propagate freely through the nothingness of a vacuum, whereas they suffer from collisions with atoms in a solid semiconductor because of a process called crystal lattice scattering. What's more, a vacuum isn't prone to the kind of radiation damage that plagues semiconductors, and it produces less noise and distortion than solid-state materials. The superiority of microwave tubes over solid-state amplifier, if I have to tell, it's manifold. A few of them are lesser heat generation due to the collision in the bulk of the device, higher breakdown limit on maximum electric field inside the device, smaller base plate size determined by the cooling efficiency, higher peak pulse power operability, ultra bandwidth performance, and they are tough, efficient, they are long-lived, and that's why it's very important for satellites. They are radiation hard, and TWTs in space have proven lifetimes of 20 years or more. Unlike solid-state devices, microwave tubes are fabricated out of metals and ceramics, which makes this inherently hardened against radiation and more capable of withstanding temperature and mechanical extremes. That's why research is going on to develop vacuum electron devices capable of operating at higher frequencies and shorter wavelengths in the millimetric wave region that can outperform the current generation of devices, providing significant defense and civilian advantages. Meanwhile, higher frequency operation brings with it vast swaths of previously unavailable spectrum. So as an example, now let's consider this collision avoidance radar available in some cars to protect them from traffic accidents. Specifications developed by auto manufacturers require this system to see a bicycle at a distance of around 100 meters. It must also distinguish the bicycle from other objects such as trees, bridges, roadside signs, and other moving vehicles. At a high frequency, such a system uses an antenna approximately 4 inches in diameter because the automobile engineers can tuck them behind the car's grille or fender or design them into the front end of the vehicle. At a lower frequency, the diameter of the antenna required to achieve the same beam width would be too big, which would require a pretty silly looking antenna mounted on the car. To cram such a radar into a small space, such as under the hood of a car, manufacturers first moved to 3.4 gigahertz, then to 50 gigahertz, and recently to 77 gigahertz. Today, the benefits come because we have developed amplifiers in that range. Next, coming to this 5G communication. 5G revolution presents some dramatic challenges to the design of communication infrastructures as 5G targets higher than 10 gigabits per second download speed using millimeter wave spectrum with multiple input, multiple output antennas. Connecting densely deployed wireless devices for Internet of Everything and very small latency time. The broadband modulation bandwidth for 5G RF transmitters, possibly even above 1 gigahertz, demands high power efficiency and stringent linearity from its power amplifiers. Additionally, the phased array multiple input and multiple output antennas with numerous RF front ends require unprecedented high integration level with low cost, making the design of 5G power amplifier one of the most challenging tasks. Compared to a solid-state amplifier, this has demonstrated that TWT is able to provide one-point to multi-point transmission at W-band frequency. Next, coming to space TWTs. You can see here between we need communication between satellites, between satellite and Earth station, between Earth station, between repeater and Earth station, between repeater and satellites. And key attributes of such power amplifiers, we need long life, mission life greater than 15 years, high reliability, low power consumption, and low mass. That's why TWTs can provide a crucial service to them. That's why they still dominate satellite communications. The number of space TWTs produced every year depends on the number of satellites launched. Since 2010, there are approximately 20 GSO satellites sent per year, and a communication satellite contains around 50 to 60 amplifiers. Consequently, there are between 500 to 2,000 space TWTs produced every year. If long-distance communication seemed impossible 100 years ago, the TWTs made it possible from outer space. That's why, though attempts were made in the middle of 1990s to replace 50% of space TWTs with solid-state amplifiers in satellite qualified systems, such replacements declined within years because of the requirement of a longer mean time before failure that could be met only by space TWTs. TWTs appeared as on one of the majority of spacecrafts. You can see if you want to replace the TWT with a solid-state amplifier, it's better to be replaced in the uplink, that is a ground-based version. But in the space-based version, a TWT is one of the best amplifier that can be used. And also, the design is now going towards higher frequencies and higher powers. And that's why TWT is still at the cutting edge of space power amplifiers, and certainly it will continue for several decades. So now, what is the lesson that I learned is, if we have to work on something that will be used for many high specialty applications, you need to make your device for that specification. That involves a lot of modification in your system. So a development of a TWT needs to incorporate all these things. If you want long life, if you want high linearity, that designing a device for use in onboard satellite applications requires a disciplined design approach and a high level of quality consciousness. As the systems on board are meant to perform for long term with no maintenance possible, reliability and redundancy in design is very, very important. Critical parameters are size, weight, and efficiency. Therefore, they have direct impacts on fuel consumption. So the development of TWT is very important thing. You can see here that TWT will consist of totally 150 to 180 piece parts. And the piece parts accuracy is from 10 to 50 microns. And you can see so many materials we use in a TWT. And so many softwares have to be used, different types, to generate a particle and cell simulation from the gun to the collector. So development of TWT include intricate labor-intensive process that require exquisite modeling tools, exotic materials, and expensive high-precision machines. It's an infinitely deep subject, and one needs the precision of a goldsmith in the development. You need physics, you need electromagnetics, you have high temperature mechanical design, you have high vacuum magnetic material science. It takes a choreographed effort across many disciplines to create one of these TWT. Starting from material selection being vacuum grade, chemical process, fabrication technologies, vacuum processes, step brazings, high voltage RF testing, environmental qualification, everything you can see, it's a process starting from the design, fabrication, chemical processing, treatment, brazing, leak checking, vacuum processing, high voltage testing. In one of the time when I was doing that, the whole It took a long time, but finally everything is over. A small leak has spoiled. So at that time, I was trying to blame my team because I was the project leader. I was trying. So that time, the director was a very nice person. He's no more now. He called me and said that if you are a good leader, you should take the blame when the problem comes, and you should give whenever anything is successful, you give the credit to your team. That is the mark of a good leader. That is the first thing that I learned when I faced that failure. Because in the TWT, you need to learn a lot of things, critical things you need to learn. Like you have electromagnetics, you have high temperature mechanical design, you have high vacuum magnetics, material science. It takes a choreographed effort across many disciplines to create one of these vacuum tube. Vacuum electronics is an infinitely deep subject. So, if you see the cathode should be activated, the TWT, it should be pumped both sides, the processing should go on, magnet should be stabilized, it should be vacuum processed, and then after processing, it should be aged. And so many things you need a test, both environmental test, electrical test, and finally, you need so many of these things. The design and development of the TWT should ensure the consistent and reliable performance over the operational life. So now, if you see, the evolution of the TWT has taken place in 4 different angles. One side, you can see it's going towards wide bandwidth. The other side is going towards high power. This side, miniaturization, and then going to the high frequencies. So now let's see one by one how we are able to go ahead with this. Now, if you see towards this compactness, now I presented before you the advantage of solid state, the advantage of microwave tubes. They thought, why not we combine both these things? So that's when microwave power module came into existence. So in this one, the advantage of solid state devices have been used in microwave power module, where a helix TWT and a solid state power amplifier coexist, sharing the gain equally in a compact system, whereas the electronic power conditioner provides a built-in power supply. Microelectronic technology have been used to realize high power devices, small devices for this. And because of this, you get overall high transmitter efficiency, miniature transmitter size, broadband power capability, high reliability, reduced cost, flexibility, volume is reduced by 1/10, weight by 1/6, RF power increased by 2.5, efficiency 5 times, reliability 3.5. So now coming to the high, this is a compactness. Now frequency. If you want to go high in frequency, there is a huge swath of the electromagnetic spectrum at frequencies between the microwaves and the infrared light that has not been fully exploited yet. This is a terahertz regime, or we can call it as infrared at sub-millimeter radiation. At frequencies between this far end of the microwaves and the lower end of the infrared. This energy in the terawaves is too low to knock down the electrons from atoms, and they do not have the potential to ionize materials, and therefore they don't damage living materials. And that's why it's very interesting. They permeate more for clouds. They cannot penetrate metals. You have a strong water line. So spectroscopy is very useful. Using this, you can find out in other places whether there is water and others. High-speed communications, and you can send a lot of data. That's why super fast communication you can have. And you can, because of which, using goggles, you can see whether mines are planted underneath. And also, you can also help people with skin cancer. So you can, in this imaging through terahertz frequencies, it's non-ionizing. You can see it's much clear. The fingerprints are much clear. And the watermark in this currency also, you can see it's very clear. That's why terahertz communication has a lot of advantage. You need smaller antenna size, high directional beams. So that's why it's used for satellite to satellite communication, because ground to satellite, you have a heavy attenuation. And also in battlefield communications, and where you need a secure communication, these things are used. Now, for a terahertz frequency, you need a different vacuum electronic technology. As you push the frequency up, you cannot use conventional manufacturing technique anymore, because high current density cathodes it has to be made and using in small area. That's when carbon nanotubes, spin type tips, all these things come into picture. So microelectronic fabrication is done based on LIGA techniques or deep reactive ion etching techniques. And in LIGA, you have both X-ray and UV LIGA techniques. Here, this is one waveguide fabricated using the LIGA technique. There are some sheet beams also you can use. This is some of the advances in cathodes. So these are some of the things. Now coming to we have seen how miniaturization, how compactness, how we go to high frequency. Now coming to high power, the quest to build an electromagnetic weapon, an E-bomb in military jargon, was sparked on the 8th July 1962 when the United States carried out Starfish Prime, the largest high-altitude nuclear test that had ever been attempted. The 1.4 megaton thermonuclear warhead detonated 400 kilometers above the Central Pacific Ocean and blasted huge swarms of charged particles outwards along the Earth's magnetic field. Their gyrations generated a pulse of microwave energy that drove measuring instruments off the scale. Artificial auroras lit up the night across the ocean, and in Honolulu, more than 1,000 kilometers from the detonation point, the pulse set of burglar alarms knocked out street lights and tripped power line circuit breakers. The test showed the potential destructiveness of an electromagnetic pulse to military planners on both sides of the Cold War. And that launched them in a race to harness it as a weapon using a non-nuclear source through that country's high-power microwave program. At first, the goal was a weapon capable of taking out an enemy's computers, communication systems, and other electronics. In theory, the idea remains compelling. An E-bomb would be able to fire microwave bullets at the speed of light, and if tuned to the right frequencies, it can disable its targets without collateral damage. Cars could be stopped in their tracks, and radars can be blinded, and computers can be destroyed. There is with no need of high explosives. But the technical challenge is it's to generate a pulse that is directed enough to pick out a specific target and powerful enough to have an effect when it gets there, ideally using a generator that is small and light for an aircraft or a missile to lift. A battery-powered device can generate a hyper microwave pulse, but producing that kind of highly concentrated pulse needed to destroy electronics typically requires detonating conventional explosive, but doing this inside a piloted aircraft is risky. The superconducting electromagnet that powered the system's pulse generator required a cooling system too big and too cumbersome to be used in the field. So that's why it's very difficult, but still the Air Force publicly, US Air Force announced in 2001 that they are going to pursue after it. And again in 2007, they tried to send this high energy microwaves at 95 gigahertz. But what happened is that particular day, it was very cold and it was rainy, and the water droplets in the air it absorbed the microwaves, and that's why the reporters did not feel the heat. But otherwise, if it would have been on a dry day, it goes almost inside the skin, because it is very safe. It goes around 0.5 millimeter in the skin, and it generates a heat, and people cannot stand before it. So it's a soft kill. So it makes the crowd to get dispersed. This is one of the applications. So now this is these are some of the sources like Whittaker's relativistic magnetron, magnetically insulated line oscillators. These are some of the sources for hypermicrowaves. Now, if you have to go into high power side, we need a different technology. You can see this is totally different technology. Now, again, if you want to get a high bandwidth with the existing klystron, you can even do multi-beams through that one. So using multi-beams, using sheet electrons, you can do it. And similarly, recent trends in high conventional microwave tubes, you can see this, the driving forces enhance system requirements. And now there is a competition with solid state. That's why we need to develop new concepts. You can see how it is evolving. If you don't adapt to the change, you will die. So high performance electron guns and high efficiency multi-stage depressed collectors and all these things we need, multi-beam devices, microwave power modules, vacuum microelectronic devices, and all these things we need. And finally, future direction. So in the commercial market, we need TVs and digital rates are demanding higher powers. Whereas in military side, we need to go higher frequency, lightweight, and for satellite, you need more reliability. So a lot of places you need TWTs and hyper microwave devices and high frequency devices. So even though solid state can be a competition, microwaves, tubes will remain. I have explained about the technical challenges we face. Now, this is a multidisciplinary field and you have engineers in different disciplines. Now, how do we adapt to these changes? I am going to explain in the next 10 minutes. See, there is a need for innovation strategy. Our researchers should be on par with the rapidly evolving technology. A teachable attitude should be there because everyone has the potential to learn. Life should be a long-term learning. So continually, we should learn to leave our comfort zone and capture much about the latest technologies. And if there is any change, the leaders should spread the word about the change to the working community, and there should be a sense of urgency about the new technologies. The existing vision, if it is added or modified, should be communicated to the lowest person, even up to the late person who is working on the lathe, and they should be empowered to act on that vision. Then leaders should be on the job to make the workforce know why they do what they do. Based on the changing situations, the leader should be flexible to adapt to changes. The flexibility can be cognitive. There is the ability to use different thinking strategies in planning, decision-making, and management, an interest in developing new approaches, the ability to see and leverage new connections, and the propensity to work well across various organizations, emotional flexibility, the ability to vary one's approach to dealing with your own and others' emotions, an area that many leaders sometimes fail to consider, dispositional flexibility, the ability to remain optimistic and at the same time realistic, and to operate and dispositional, to operate from a place of optimism grounded in realism and openness. So coming next in the study by Duckworth, Peterson, Matthews, and Kelly in 2007, one prominent characteristic was found among the most successful leaders across different settings. What was that characteristic? It's grit. Grit is defined as perseverance and great passion for long-term goals. Grit involves working persistently towards challenges and maintaining effort and interest over the years despite failure, adversity, and plateaus in progress. In other words, someone who is gritty approaches every situation as if it was a marathon. That is internal motivation. And also they will have an end goal for the task that they have taken. That is external motivation. So this is the one they have checked across various populations and found this was true across various different populations. And they also believe that this grit is linked to a growth mindset, which is an idea that the ability to learn is not static and it is fluid. And a person with the growth mindset believes that basic abilities are developed by perseverance and hard work. In addition, individuals with a growth mindset persevere through hardships because they understand that failing is a part of learning. It's not an eternal. As a result of a growth mindset, learning becomes enjoyable and resilience is developed. So now many of us are afraid of failures, but I learned that failure stories are not taboos, but helps us to be forerunners. Every failure, how we are able to explain about our success, it should be more than that. We should document each and everything. Might be some small puzzle is missing. So if you don't document, another person will take up that same project. They also will fail. So it's better to document. And also there should be a free flow of ideas across the organization. People should not feel that somebody will take their credit and log their ideas. So it should be a free flow. That's very important. And risk management strategies to be taken up. And next is important thing is to really drive performance. You want to develop leaders at all levels, not just average leaders. I'm talking about exponential leaders who know they are aligned with the organization's vision and mission. They are deeply rooted and it's beyond simple ownership. And they want to drive the organization towards excellence. If you want to develop such team of leaders, here are a few characteristics of the culture we need to harvest. We need in that culture, we should have integrity, trust, empowerment, alignment, engagement. When these elements are in place, we will be able to develop a culture that fuels our ability to achieve much more. And the only way we can do is that by developing leaders at all levels. So man is a social animal, and that's why interpersonal skills development is very, very important. How do we develop it? We need to listen. We need to give feedback. We need to learn to handle the conflicts. And the trait of a successful leader will be an enthusiasm. They'll have a lot of enthusiasm. That effective leaders require a proactive approach towards the people. Some of the lessons that I've learned is unless we get all these things in our heart, unless we be a change maker, unless we do all these things, we might not be able to navigate towards the difficult projects, difficult changes that are needed in the organization. Because we need to evoke excitement among people so that the organizational goal should be achieved in an exciting manner, in an energetic manner. And that's why the leader should know their weakness and they should be vulnerable to speak about it. And that they should be very good in decision making. They should be open enough with mutual respect. And it should not be, power should not reside in one place, but people should be empowered. And the leader should be able to inspire and motivate. And the goal should be properly understood. Character is a constant effort to integrate your words and actions. Character is what you do when no one is watching. One man should be same both in secret and public. So vision should be protected by values. So that is very, very important. Leadership is not a position, but a process. And the next one is leaders should know how to equip people who grows other people. What you do has far greater impact than what you say. So that's when leaders should be able to also manage the conflicts. Many times we hold a mistaken belief that the conflicts are all wrong, but professional conflict is good. When somebody comes with a different design, we should be open enough to accept it. And we should be open enough to understand that other designs are better than mine, and so we will work on that. So that's a professional conflict. But there is a personal conflict. It can be because of interdependence. It can be because of differences in our styles, our gender, or preferences, or even in our leadership style. Somebody can be can delegate easily. Somebody cannot. Somebody can accommodate. Somebody cannot. So these are the personality clashes can come. But many times we hold a mistaken belief that conflicts will never exist if annoying people would stop annoying. Unfortunately, when we operate with that belief, we tend to say things that somebody is responsible for that. But it is not that. We have to look at the structures that lie underneath the conflict. And because once there was a conflict between two people, while others described to me as a communication problem or a personal conflict, when I discussed with them, they told me a different story from their description. It looked that it is about the opinion, how the work should be done in the project based on their beliefs about each other's functional roles. Many times when you look at conflicts, we can see deeply embedded structures, everything from the company's history and cultural norms to work processes and procedures. That's why it's unrealistic to blame individuals. Sometimes we have to sift fact from story. We think my boss is not looking at me, my boss is angry, but can we Is it a fact or is it a story we are telling to ourselves? We should know if you are telling a wrong story, we should change it to the fact. So we should have a better communication, control our emotions, stop assuming, and think of positive ways, be calm under stress, and seek advice from people with experience. These are some of the things that I've learned. And coming to the final thing for a leader, I understood 3 things. A leader should know how to inspire. The inspiration is the main skill needed to make people feel important. It's not about the leader, it's about the follower. It's a secret to succeed in life. How I make people important? Because when I give importance to my team, they will work till the end. So that's why if we do mistake, it's better to own it. Influence is anytime we seek influence, that we influence the thinking of others and we make them to do work for the project with full heart. Even though they don't like to do, they will do because of the influence. Impact is about doing. It's about working along with them. Actions speak greater than words. Great leaders lead by example. You know, during World War I, George Patton led his troops by walking in front of them. Next way one can impact is by authenticity. Authentic leaders work for their character. They walk the talk and they're aligned with their core values. So that is why it's all about impact, influence, and inspiration. And many times we need to change our leadership style based on the situations. Sometimes we should not think about our status or positions. Leadership is to encourage somebody else, and we should foster a culture of excellence. It's a skill. We love the people. They should be like brothers, sisters, and nobody is going to hurt if we treat them in that way. People will turn down even better jobs to work for this one because of the culture, of the love that is present. That's what I learned from all the things. It's very important. Leadership is everything. It's a state of mind. It's not a position. It's not a place. It's a process. So leadership has to develop all these things. And now, what are the transformational strategies that enable a leader in new effective ways? 4 transformational strategies. Attention through vision, meaning through communication, trust through position, confidence through respect. Organizational excellence requires leaders to communicate the vision in a way that induces other people to work. And communication is the primary way in which any individual can motivate the team. And trust, a key factor in the process of establishing trust is by integrity, honesty, and giving freedom and confidence. They develop confidence, the confidence that this leader is worthy of my respect. And finally, they act as role models rather than trying to push the things. They are the role models. So that's why guiding principle is change your vocabulary if we are not that. I have learned initially I was different, but now I'm different. Think big, build simple, act now, discover talents and teams, focus on relationships. 2 roads diverged in a yellow wood, and I took the one less traversed. I always wanted to go against the stream, and that has helped me sometimes, that has not helped me. And finally, as a woman, I wanted to say that I faced problems as a woman sometimes because initially when I joined my lab, my colleague was telling that, ladies, you finished it with honors because you might have mugged up and studied. That's when I struggled to get into IISc. And then I did not get into electronics. Then finally I got in an aerospace department, and I had learned to study missile guidance, aerospace vehicles, and many things else. So that's when God helped me to do that. But when my children were young and I had to study and I had to work, I fell into serious depression. And once I got a severe pneumonia and I was put on ventilator, people thought I've died. And I met the God of the universe, and I heard a voice, I'm giving you new life. That changed me. That's when I understood that running up and up in the ladder of your promotion is not that great important than your life. When you are living, try to give more importance to others, lift them up. Even this COVID has shown me that how important is our life, how we have to treat others, and instead of pushing others to come up in the ladder. That's what I learned in my life. Any questions?
There are some questions in the chat box, madam.
So somebody is asking one question, how to build and quality of such complex systems from design to service stages. Yeah, it's a multidisciplinary field, slightly difficult. That's why many times we are prone to fail. But unless we incorporate the risk management system into place, learning to document failures and learning to understand from our mistakes and how to work with various teams who are in various departments, it's very difficult to win the game.
If the participants have any questions, they can please speak up.
Latha ma'am, this is Suma from VSSC.
Yeah.
Are you audible?
Yeah.
I would like to ask you one question related to the launch vehicle technology. Currently, we have already replaced all the TWT with the semiconductor devices, active devices. Then is it possible to revert back as per?
Might be the new your satellites, you can use TWTs because the life of such devices are quite low compared to TWTs, and the efficiency is low. Might be you have catered to that that specification. I'm not sure, and how it is in ground, you can replace it, but in space, I'm not sure how would you do it. But in ground-borne radars, you can replace that.
Another question I would like to ask: where any industry is there in the micro TWT fabrication and all?
So we are we are doing at present. Siri, Pilani, they are working on that, and Samir also is doing some work. So these are some of the people who are working on, and Bharat Electronics is working on that.
Thank you, ma'am. This is a wonderful talk. All areas you cover, all the management lady, all the areas you covered is an excellent talk, ma'am. Thank you so much.
Thank you.